properties of determinants. So let's see the first property, that is, if any row or column is 0, then the determinant is 0. What does it mean? First, suppose if A is a matrix with the elements 0, 0, 0 in any one row, I'm assuming it in the first row. The remaining rows elements can be anything like 5, 2, 1, 7, -1, 3, anything. Then the determinant of this matrix will be 0. Why? Because when you actually calculate its determinant, how to calculate its determinant? Take its A11 element with M11, take its A12 that is 0 with M12, and take its A13 that is also 0 with M13. So something you multiply with 0, you will get a 0 itself. So finally you will get answer as 0 only. So auntie ho gaya auntie. So basically if you multiply any, if any row or column has 0 elements, so basically if any row or column has value of element is 0, then the determinant will be 0. Coming to the second property, which says if two rows or columns have equal or proportional values, then its determinant is 0. For example, if the determinant A is like this, A1 like A, B, C, D, E, F, and again A, B, C. If this is the elements in the determinant, then this determinant will be 0. Why? Because if you observe, the first and the third row in the determinant have the equal values. So the determinant will be 0. Or, first suppose, if the determinant is like something like this. 2, 3, 4, some 7, 8, 9, 4, 6, 8. Then this determinant value is also 0. Why and how? When you take common from this, from where you can take common? From the third row. The first and the second row will remain as it is. If you take common from the third row, 2 value, because third row is something like 2 into 2, 2 into 3, 2 into 4. So if you take this 2 common from the third row, we can write this 2 outside. So if you observe, again this first and the third row elements have equal values. So it was nothing but 2 times of 0, which is nothing but 0 itself. So basically, if any 2 rows or any 2 columns have the equal or proportional values, then its determinant is always 0. The third property is value of determinant changes by a minus sign if we exchange any 2 rows or 2 columns. For example, if the determinant is something delta 2 minus 3 5 6 0 4 1 5 7 minus 7. So let us calculate its determinant. So what it will be? A11 M11 is 0 4 5 minus 7 minus of minus 3 and 6 4 1 minus 7. Sorry, its determinant. Next, plus A13 that is 5 n13 is 6015. So let's simplify this. 2 into 0 minus 20, it becomes plus 3. 7 6 are minus 42 minus 4 plus 5, 30 minus 0. So it becomes minus 40. So minus 138 plus 150. So something you'll get it as minus 28. Now let us interchange row 2 with row 3. So this is nothing but, this symbol is nothing but interchange symbol. So if we do that, it becomes d dash, something delta dash 2 minus 3 5. Interchanging row 3 matlab the row 3 elements will come to row 2. That is 1 5 minus 7, and row 2 elements come to row 3, that is 6 0 and 4. Now let us calculate its determinant. So it becomes 2 5 minus 7 0 4, minus of minus 3, and here 1 minus 7 6 4 plus 5 1 5 6 0. Now just simplify this, you'll get 2 20 minus 0, minus into minus plus 3 4, minus into minus plus 7 6 are 42, and 5 0 minus 30. Now you'll get it as 40 plus 138 minus 150, that is nothing but plus 28. Plus 28 is nothing but minus of delta from here. So here from the property 3, we can prove that value of determinant is changing. By how much? With a minus sign. So what's the relation between delta and delta dash? Delta dash is nothing but minus of delta, or delta is equal to minus of delta dash. Why it's changing and when it's changing? When you are interchanging this two rows, that is row 2 and row 3. You can also verify it by changing row 1 and row 2, or also you can change the columns, that is C1 with C2 or C1 with C3 or C2 with C3. Anything you can change, but the answer you're going to get a negative sign of this. The fourth property is the value of determinant remains unchanged. It doesn't change if its rows and the columns are interchanged. So basically, for example, the determinant A, that is 1 0 minus 1 2 4 6 3 5 and 0. So if we calculate its determinant, that is A11 into M11 minus A12 is 0. So obviously, if you multiply anything it with 0, you'll get a 0. So next it is A13, that is minus 1 into M13, 2, 4, 3 and 5. So when you simplify this, you'll get 0 minus 30, and this is 0, this is minus 1 into 5 2s are 10 minus 12. So how much it becomes? Minus 30 minus of minus plus 2. So it's nothing but minus 28. So now let us interchange rows and columns. What does this statement mean? You are just interchanging the rows with the columns, and now the columns becomes the rows. Basically, now A dash will be, this is a row number 1. So now it becomes column number 1, that is 1 0 minus 1. Now row 2 becomes column number 2, 2 4 6, and row 3 becomes column number 3, that is 3 5 0. So if you basically see, observe over here, the column 1, that is 1 2 3, became its row 1, right? And the column 2 became row 2. and the column 3 became its row 3. Now let's calculate its determinant now. So it is 1 into m1, 1 is 4, 5, 6, 0, minus 2, 0, 5, minus 1, 0, plus 3, 0, 4, minus 1, 6. Let's simplify this. 1, 0 minus 30, it's minus 30, minus 2, 0 is 0, and minus into minus plus 5, plus 3, 0, minus into minus plus 4. So it just becomes minus 30, minus 10, plus 12. So it's nothing but minus 28. So if you observe over here, the value of A and A dash are equal. But we have interchanged the rows and columns. So this property says that whether if you change the rows with the columns or the columns with the rows, the determinant do not gonna change. It remains as it is. So this is a very important property which helps you in the question solving. So make sure you know about this. The next property is elementary row or elementary column transformation do not change the value of determinant. What is elementary row transformation? We have already learned this concept in the matrices chapter. So you are changing any row by adding its multiples of remaining two rows. For example, here row 1 can be changed with row 1 plus alpha times of row 2 plus beta times of row 3. Similarly, it goes with the column. So here alpha and beta values can be anything. It might be same sometimes, it might differ. One can be 0, one can be negatives, anything. For example, if alpha is 0, then we'll write R1 changes to R1 plus beta R3. If beta is minus 1 and alpha is 2, we'll write R1 plus 2R2 minus R3. If beta is 0, then we'll write R1 plus alpha R2. So you need to observe over here is, in all this kind of transformation, the value of R1 is not changing. We are not multiplying anything with the value of R1, right? But we can change the multiples of R2 and R3. So for this, let's see our question. This is a very, very, very important. Okay. So let's see the questions related to this property. So in this question, we need to find the value of this determinant and four options were given. So how can we use the fifth property over here? So if you observe over here, the first transformation we can apply is R1 can be changed to R1 plus R2 plus R3. Why? Because after doing this transformation, we can take something common from this. How? Let's see. The R1 element, that is A11, 2C, now becomes 2C. R1 is nothing but the same element, 2C plus R2 is A minus B minus C, R3 is 2B. For this element, this is the R2 and this is the R3. For this element, this is R2, this is R3. For this element, this is R2 and this is R3. So go in that flow. Now when you do this, what the value will get? A plus B plus C. Similarly, this value 2C, again when you do that, 2C plus 2A plus B minus C minus A. Again, this value also is nothing but A plus B plus C. Similarly, C minus A minus B changes to C minus A minus B plus 2A plus 2B. This value is nothing but also A plus B plus C. Now, the determinant value becomes A plus B plus C. Here also A plus B plus C. Here also A plus B plus C. The remaining two rows will remain as it is. 2B B minus C minus A 2B. So from here, when you take common of A plus B plus C outside, it becomes like this. 1, 1, 1, A minus B minus C, 2A, 2A, 2B, B minus C minus A, and 2B. Now again, you can perform the column operations now. How to do that? Here we can do C2 changes to C2 minus C1 and C3 changes to C3 minus C1. Why this? Let's see. C2 is nothing but this column, C3 is this. So C2, here the 1 changes to 1 minus C1. For this C1 is this. So it's nothing but 0. Similarly, 2A changes to 2A minus A. This is minus of this, right? So it becomes plus B plus C. Now this becomes A plus B plus C. Now this B minus C minus A changes to B minus C minus A and minus of this 2B. This is nothing but minus of A plus B plus C. So this is all about C2 operation. Now if we talk about the C3 transformation, this column 3, 1 changes to 1 minus 1, which is nothing but again 0, and 2A changes to 2A minus of this whole thing. So minus A plus B plus C, which is nothing but A plus B plus C. And this 2B changes to 2B minus this 2B. So it's nothing but 0 again. Now the value of determinant becomes from row 1, the column 1 remain as it is because we didn't perform any column operation on this column 1. Now the column 2 changes as 0, A plus B, and minus of A plus B plus C. Column 3 changes to 0, A plus B plus C, and 0. Now if you observe again, from the column 2, you can take A plus B plus C common, and from the column 3, you can take one more A plus B plus C common, and outside we already have A plus B plus C, right? So if you take one here, the outside becomes A plus B plus C whole cube, and the remaining elements will be 1, 0, 0, A minus B minus C, 1, 1, 2B, it becomes minus 1 and it becomes 0. Now this will be easier to calculate the determinant. Now what it becomes? Outside it is already A plus B plus C whole cube. Now A11 that is 1, M11 that is 1, 1, minus 1 and 0. A12 is 0, A13 is also 0. So we don't need to take care about these values. So it becomes A plus B plus C whole cube. Now this 1 into 0, 0, minus into minus plus 1. So it's nothing but A plus B plus C whole cube. Let's see the options now. So option B is the correct answer to this question. In this question, matrix A is given and determinant of A square is given, that is equal to 25, and we need to find the value of mod alpha. So first let us find the determinant of A. So it's nothing but 5 into alpha, 5 alpha, 0, 5, minus 5 alpha, 0, 5 alpha, 0, 5, plus alpha, 0 alpha, 0, 0. So it's nothing but 5 alpha, minus 5 alpha into 0, plus alpha, this 0, this is also. So it's nothing but 25 alpha. Now, a condition is given, that is determinant of A square value is given, that is equal to 25. Now this can also be written as determinant of A into A. A square is nothing but A into A. Now, just now we have seen a property. What property we have seen? Determinant of AB is nothing but determinant of A into determinant of B. So similarly, this can be written as determinant of A into determinant of A. That is equal to 5 determinant of A square. Now just equate the value with this. So determinant of A square is nothing but 25. Determinant of A, what we have got? 25 alpha whole square equal to 25. So from we'll get 25 alpha is equal to plus or minus 5. Alpha will be plus or minus 1 by 5. But according to option, there is only one option which satisfies this. So option A is the correct answer to this question. The fifth property over here is determinant of AB is equal to determinant of A into determinant of B. And make sure here both A and B should be a square matrix. Because when we talk about the matrices, if it is A is a 2 cross 3 matrix and B is a 3 cross 2 matrix, then the output we will write it as AB 2 cross 2. But here it doesn't work like that. Both A and B should be compulsory. It should be a square matrix. And sixth property is determinant of A transpose is equal to the determinant of A itself. This is a very important property which can be directly applied in the questions. So make sure you know about this. Seventh, this is also an important one. Determinant of Ka is equal to K power n into determinant of A, where K is a constant over here and n is the order of a matrix. So to prove this, first suppose if matrix A is A1, 1, A1, 2, A1, 3, A2, 1, A2, 2, A2, 3, A3, 1, A3, 2 and A3, 3. If this is a matrix and now if you multiply a constant, first suppose 2 to this, so you are multiplying a constant to the whole matrix. So it's get multiplied with each and every element in the matrix, right? So this is a 2A matrix. But now you need to take the determinant of this. That is determinant of 2A will be determinant of 2A11, 2A12, 2A13, 2A21, 2A22, 2A23, 2A31, 2A32 and 2A33. Now, I've already told you when you are taking a constant common from the determinant, you need to consider it either row wise or the column wise. So when you are taking 2 common from here, so from the row 1 you need to take 1 2 common, from the row 2 you need to take one more 2 common, and from row 3 you can take one more 2 common. So it becomes 2 into 2 into 2, A11, A12, A13, A21, A22, A23, A31, A32 and A33. So it's nothing but 2 cube. This is nothing but the determinant of A itself. So here 3 is nothing but the order of matrix. What is the order? 3 cross 3. So n is the order of the matrix. So this is how we can prove this. So let us see few questions on these properties.